Thank you. Well, okay, Brian's gone, but I was going to thank him for inviting me to come and speak, and thank you all for turning up today. My name is Catriona Murray, and I'm originally from Scotland, but I moved to Boulder about a year and a half ago. And I'm a postdoctoral researcher at the University of Colorado Boulder. And for my PhD, I worked, as Brian said, on the Speculoos project, which is a ground-based survey trying to detect planets around about the same size as the Earth in the habitable zone. Oh, thank you. Is it possible to dim closer to the screen? Great, okay, see it better. So I was working on trying to find planets as part of my PhD, and then for my postdoc, I'm now trying to take the planets that we know about and try and figure out what's in the atmospheres of those planets. So I'm going to take you on a little bit of a whirlwind tour through the work that I've done, both in how do we find good candidate exoplanets. So exoplanets meaning planets outside the solar system. How do we find good candidate exoplanets for follow-up with telescopes like JWST? How do we actually see what's in the atmosphere of a planet? What is JWST? And what's the work that I've done specifically towards it? And what do I see as the major challenges moving forward? Okay, sorry, I lost the mouse. I think we're good. So the most basic part of my talk is how do we find planets? So what we do essentially is what you see here. When a planet passes in front of its star, it will block some of the light from that star. We see the shadow from the planet. And this is actually a measurable quantity. So we call this the transit detection method. And the amount that the starlight will dim is related to the ratio of sizes between the planet and the star. So the bigger the planet or the smaller the star, the more we see the light dim. If we had a planet the size of Jupiter orbiting something the size of the sun, we're going to see about a 1% dimming, which is very measurable by ground and existing space-based telescopes. But if we have something the size of the Earth transiting something the size of the sun, we're going to get something about a factor of 100 times smaller. And so that is actually currently beyond our capabilities. And so we're going to have to wait to the end of the decade for missions like Plato to be able to find these kind of systems. So we can get a lot of observable parameters from a transit or an eclipse. We can get information about the timing of the system. We can learn about the orientation based on the shape of the transit. But what we cannot get from the transit method is the mass of the planet. It does only tell us about the size, nothing to do with the mass. For this, usually we have to follow up with an alternative method like radial velocity, which is where the planet will exert a small gravitational pull on its star in the same way that the star obviously pulls on the planet. And we can see that little wiggle there, and that can tell us about the mass of the planet. Another disadvantage of the transit method is that we have to actually be very lucky to have the planet line up perfectly for us to see the eclipse. In a lot of cases, the planet doesn't actually transit at all. So when we talk about finding planets, we usually care about planets that are going to look like Earth. So a proxy for that we use is looking for planets in the habitable zone of a star. And so the habitable zone essentially just means planets that have the ability to have liquid water on their surface. And so for a star like the sun, we're going to be waiting, a year to see every orbit from that planet. But if we move towards smaller stars and therefore cooler stars, so I'm going to call these red dwarfs or M dwarfs, then the habitable zone actually shrinks inwards to periods of only a couple of days. Additionally, the closer a planet is to its star, the higher our chance of seeing it, because we get sort of a bigger spread of that shadow. So I'm going to try and combine all three of the last slides into one plot, which is a little confusing, I'm sorry, on the left here. So we have the probability of seeing a transit in yellow, the transit depth, so that's related to the size ratio between planet and star in blue, and the number of orbits per year. And this is specifically for an Earth-sized planet in a habitable zone of its star. And on the x-axis here, we have the mass of the host star. in terms of mass of the sun. So 1 here is a sun-like star. And so as we move to lower mass stars, we can see that all 3 of these kind of observable parameters that we care about all peak. And I've highlighted this pink region here, which I'm going to call ultra-cool dwarfs. So essentially, ultra-cool dwarfs are stars that are about 10% the size and mass of the sun. They're much, much cooler than the sun. They have luminosities also about 10%. And they have temperatures less than about 2,700 Kelvin. So these are a very specific kind of object. And I'm going to highlight some planet detection surveys on here to kind of show you where they exist in this parameter space. So TESS is a NASA space-based telescope that was launched about 5 or 6 years ago at this point. And they can look at everything from sun-like stars down to about mid-M dwarfs, so a little bit bigger and hotter than ultra-cool dwarfs. MIRF was the first kind of M dwarf focused project that started in 2008, but they are a ground-based survey and so had issues. When we look at these cool stars, they are quite red. So we have to go into kind of the near infrared wavelength regime to be able to see them. And when you're in that regime, the Earth's atmosphere has a bunch of annoying absorbing molecules like water vapor. So MIRF had a lot of issues with water vapor in the Earth's atmosphere. Then Speculus, which is the project I was involved with for my PhD. They are also a ground-based mission, but they started later and also had slightly different observing strategy and different equipment to be able to deal with the Earth's atmosphere. So we stretch all the way from mid-M dwarfs right down to even brown dwarfs down here. More recently, in the last couple of years, we have the Pines and Eden survey. They're very, very new. So they don't have a lot of data results yet, but they kind of span subsets of that Speculus region here. So if this is on the left, just tells us about the detectability of planets, but on the right, I've totally ignored this plot so far, but we've highlighted some spectral features we might want to care about in a planet's atmosphere. So water, methane, ozone, carbon dioxide. And we see the detectability or the signal to noise peaks also in this pink ultra-cool dwarf regime. So not only are these planets easier to find, but they're also easier to characterize. So I'm going to try and summarize all that sort of dump of information in what I'm going to call the ultra-cool dwarf opportunity. The M dwarf opportunity is a well-known phrase in my community, but I'm trying to convince you we want to go even cooler than that. And so essentially, it is easier to detect Earth-sized habitable zone planets. It is also easier to detect spectral features in the atmospheres of those planets. I haven't touched on this so far, but late M dwarfs, like M dwarfs and cool stars, tend to make up the vast majority of our local stellar neighborhood. So there are more stars to look around. And from Kepler, we have predictions at least about the occurrence rates of planets around those stars, and we know that they should host more planets than, for example, sun-like stars. But I don't want to tell you that this is the only place we should look for planets, and these are perfect host stars. They are not. They are more active. They flare frequently and energetically, and those nice close-in planets that we care about are therefore much closer to the star and being bombarded by a lot of energy from the star. We also don't understand ultra-cool dwarfs very well because they haven't been studied in a lot of detail before. They are hard to observe from the ground because of the Earth's atmosphere. And sort of more abstractly, if we find a habitable zone planet around an M dwarf star, it's going to look different to the solar system. It's very easy for us to say we know of life on an Earth-sized planet around a sun-like star because that is us. But if we find a habitable planet around an M dwarf, we don't know how to compare that to what we see on Earth. So I mentioned the Speculus survey. I want to very briefly just talk a little bit about that, about the survey and the results that have come out of it. So Speculus is a European, but now kind of worldwide survey that stands for the Search for Habitable Planets Eclipsing Ultra-Cool Stars. And it's a ground-based transit survey looking for planets around about 1,700 objects of these red dwarfs, these objects type M6 and later. So the project actually began over a decade ago with a prototype survey of 50 cool dwarfs on the 60 centimeter TRAPPIST South telescope in La Silla, Chile. Not long after this, in 2016, they discovered the 7-planet TRAPPIST-1 system. And some people may have heard of this system. It's 7 Earth-sized planets around a cool star, and it quickly became one of the most well-discussed candidates for atmospheric characterization in the era of JWST. More colloquially, we refer to this discovery as Speculus 1 because it was the first official system found as part of the Speculus project. Over the next few years, we completed commissioning on all the Speculus telescopes, and they began official scientific operations in 2019. So we have the Speculus Southern Observatory in Paranal, Chile, with 4 telescopes. We have the Northern facility in Tenerife with 1 telescope, and we have Santex in Mexico with 1 telescope. The project is also aided by observations from the 2 TRAPPIST-1 telescopes that are a little smaller for the very brightest targets. So I just want to briefly talk about the sort of main results that have come out of the Speculus project, as well as some of the planetary systems they found. So I mentioned there's about 1,700 targets. This is split into 3 different scientific programs. In the context of this talk, what we really care about is program 1, which are the 365 dwarfs, small and nearby enough to make possible a detailed atmospheric characterization of a potentially habitable Earth-sized planet. Program 2 capitalizes on the synergy between Speculus and TESS, the TESS telescope I mentioned earlier, by targeting sort of M5, M6 type objects, for which we'd get a significant detection of a planet like TRAPPIST-1b, which is the most inner planet in the TRAPPIST-1 system, with TESS. Program 3 essentially is everything else. So the goal of program 3 is to perform a statistical census of short period planets around all ultra-cold dwarf stars. So the observational strategy with Speculus is to observe each target for 100 to 200 hours with the network, depending on the scientific program that that target is in. So, as I mentioned, the main goal of the Speculus project is to find good candidate exoplanets for JWST. One of the best systems out there is TRAPPIST-1. So TRAPPIST-1 is 7 temperate terrestrial planets around a nearby M8 star. So this is a very cool star. I'm not going to go into a lot of detail about TRAPPIST-1 because there's a million talks out there and people more qualified than me to talk about it, but it's already been studied in cycle 1 proposals for JWST, as well as the subject of many cycle 2 proposals as well. But what I want to talk about a little bit more is the Speculus 2, which was the second system found as part of the Speculus project, which is a nearby late type M dwarf with 2 transiting temperate super Earths. So those are planets slightly bigger than the Earth. And the inner planet was actually originally found by TESS as a planet candidate, and then it was followed up with the Speculus project to confirm the inner planet B, as well as detect a new planet C that was beyond the reach of TESS. So I want to kind of show you these 2 systems in context against planets around cool dwarfs. So we can see Speculus, I tried to highlight them with arrows here, but Speculus 2 is here and TRAPPIST-1 is down here. And they're the 2 coolest known planet hosting stars that we know of. We actually don't know very many planetary systems with hosts lower than 3000 Kelvin. So this is the temperature of the host on the y-axis, and then the instant stellar flux the planet receives on the x. 1 here would be the same flux that the Earth receives. So we've marked on the inner and outer limits of the habitable zone, red being the inner limit, the optimistic inner limit, blue being the outer limit, and green being a conservative inner limit. I can talk about that more in detail if anyone's interested, but the TRAPPIST-1 system has at least 3 planets in the habitable zone of its star, and Speculus 2c actually lies directly on the conservative inner limit. And this is a really interesting location because this is where we think that the runaway greenhouse effect might start to take place. So it would be a really interesting test location to study an atmosphere at this distance from its star. Interestingly, all of these very coolest systems are all multi-planet systems, meaning that the star hosts more than 1 planet. And then I want to show you those systems again, those planets again, but related to other temperate terrestrial planets, not necessarily around cool stars. So on the y-axis, we have typical transmission signal So that's what we're looking for when we want to find atmospheric signals in an atmosphere. And then again, the instant stellar flux on the X. And the color bar is just the detectability or signal to noise relative to TRAPPIST-1b. TRAPPIST-1b marks our kind of gold standard. Essentially, it has the most detectable features of any planet that we know about, or at least any temperate terrestrial planet, I should say. So we can see the TRAPPIST-1 planets up at the top here all have very high detectability, very large transmission signals. But the Speculus-2b actually compares pretty nicely with the outer TRAPPIST-1 planets. It's likely too hot to have an atmosphere, but it still could be a really interesting object to study. And then Speculus-2c actually is the most favorable habitable zone planet outside of the TRAPPIST-1 system for atmospheric characterization. So both of these systems, I think, will make really interesting targets for JWST. So obviously the Speculus project is aimed at finding planets, but because these are objects that have been very hard to observe, these ultra-cold dwarfs, we've actually had a lot of really cool ancillary science come out of it. So we've been able to detect novel ultra-cool systems, such as the first ever detection of an eclipsing substellar binary in a young triple system. We've been able to shed light on the mysterious magnetic behavior of these stars, for example, studying their flaring and rotating activity and constraining their stellar spot coverage. We've been able to refine planetary parameters and transit timing variations of known planets, such as the TRAPPIST-1 system here. But actually, one of the biggest things we've been doing is performing follow-up photometry for other surveys. So, for example, we've been able to help confirm planetary candidates, such as this one for TESS, as well as interesting stellar systems like this one for NGTS, as well as follow-up for KOPS, K2, and WASP. So we found a planet. Now we want to look at what's in the atmosphere. So we use a method very similar to the transit method that I described, but what we want to do is we want to split that light into different wavelengths. So when the planet passes in front of its star, the light from the star is actually filtered through that planet's atmosphere. And depending on what's in the atmosphere, we're actually going to see the planet is slightly bigger, because if something is absorbing in the atmosphere, it's going to appear opaque. So we're going to see a slightly bigger planet than we would if we didn't have an atmosphere, for example. And so by picking apart the size of the planet at different wavelengths, we can build up a transmission spectrum. So this method's called transmission spectroscopy. And using it, we get a transmission spectrum like this. So this is just an example of what you would get if you had something like the Earth. But essentially, it tells you the blueprints of what's in an exoplanet's atmosphere. So, for example, at a certain wavelength, you might see a dip, and we know that that dip is related to the absorption from carbon dioxide in the atmosphere, or methane, or ozone, or water, etc. Okay, and then so how do we try and get these transmission spectrum? Well, we use an instrument like JWST. I've mentioned JWST so far, but I haven't actually explained what it is. So it is a near to mid infrared space telescope that was launched on Christmas Day 2021. It has 4 instruments on board. It has 3 near infrared instruments, NIRCam, NIRIS, and NIRSPEC, as well as one mid infrared instrument called MIRI. It has a primary mirror consisting of 18 hexagonal segments. Each is made of gold-plated beryllium, and combined together, they make a 6.5 meter diameter mirror. By comparison, Hubble had a 2.4 meter diameter mirror. So that gives JWST a collecting area of about 6 times that of Hubble. It can also detect objects up to about 100 times fainter than Hubble, and also go back in time a lot earlier in the universe than Hubble could. And so part of the reason for this is the wavelength coverage. So this is just to kind of put James Webb or JWST into context. Hubble went from the UV through the visible just slightly into the near infrared. JWST goes from visible to the mid infrared, and Spitzer, which is another NASA space telescope, went from mid to far infrared. So JWST kind of bridges the gap between Hubble and Spitzer. And that's important for a number of reasons. So interstellar dust is more transparent in the infrared. We can look at cooler objects such as planets. We can also look back further in time. There's a number of good reasons we want to look in that regime. So JWST does a lot of science that is not related to exoplanets. I'm going to ignore all of that science and just focus on exoplanets and specifically transiting exoplanets that I've talked about. As I mentioned kind of at the start of this talk, I had the chance to work with JWST data as part of what we call the early release science team, or ERS team. I'm kind of going to refer to it as throughout the rest of the talk. And so the early release science program was started before I even started my postdoc. And the goal was to kind of collate resources, like collect together expertise and knowledge and tools to be available for as soon as the data came down from the telescope. The telescope was launched in Christmas 2021. The first data results didn't come back down until the following June. So there's about 6 months there where it was in the sky and we didn't have any data. So this program was really to try and hit the ground running as soon as the data arrived. We'd be able to analyze it and analyze it well. So just in the ERS transit team alone, there are over 350 people on this Slack channel that I'm on. So it's a very large collaborative effort from people all across the world. And the focus of the kind of first results to come out was the planet WASP-39b. And this is a gas giant planet. It's about the size of Saturn, but it's puffy. And it orbits a sun-like star that's about 700 light years away. The reason for choosing this planet was that we had previous observations from other telescopes like Spitzer and Hubble that had already revealed the presence of water vapor, sodium, and potassium. So we knew that it had detectable absorption features, and we could also compare to those other telescopes. We also knew it had a relatively quiet host star, so we weren't going to have to deal with stellar contamination. So there was a special edition of Nature published back in February with 5 papers from just this one observation. So we had an initial kind of first look, quick look paper, which was the identification of carbon dioxide in an exoplanet atmosphere. And this was actually the first clear evidence for CO2 in the atmosphere of a planet outside the solar system. And then there were 4 separate instrument mode papers. So there are only 3 instruments being used here, the near-infrared instruments, but we have 4 modes. So again, I can explain this more clearly later if it's confusing, but with near spec, we have 2 different modes, which they have different wavelength resolutions and coverage as well. So there's 2 near spec modes here. There's a NearCam and Nearest. I specifically worked on NearCam and Nearest data. So I can answer questions about near spec, but I'm not going to be the expert on that one. So we had the first detection of carbon dioxide, but we also had the first observation of sulfur dioxide in an exoplanet's atmosphere. And this means we have the first evidence for photochemistry going on in an exoplanet's atmosphere. Or photochemistry meaning like chemical changes influenced by the light of the star. So I showed you, this is sort of similar to that video I was showing you earlier, but this is real data from JWST. This is for WASP-39b, the planet I'm telling you about. And here is the transit light curve split into 3 different wavelengths here. And you can see the very, very slight change in transit depth as we move to different wavelengths. So the green sort of deepest light curve here, deepest transit is about 4.3 microns. And it is deeper because the planet's atmosphere has blocked more light at this wavelength because of CO2. And so you can see why we need the precision of JWST to be able to measure these very, very slight changes. I've worked on ground-based data before and it looks nothing like this. I can tell you that. This is essentially model data. It's really incredible. So these were essentially the kind of results from the 4 papers in one plot. So it's a little small for you to actually see what is written there, but I'll try and highlight a few features. So each of these is one of the instrument modes, the near spec modes on the bottom, NearCam on the top right, and Nearest on the top left. Near spec prism, which is one at the bottom right, it covers the widest wavelength range, but it has the lowest resolution. So we aren't going to be able to capture really narrow features here, but we can get the general, like this big CO2 bump here. We can get this water and CO feature in here. But we're going to struggle with, for example, we don't detect potassium in near spec, which is this very thin line here. And we don't get a significant detection of sulfur dioxide, but we get a slight detection, but not significant enough to just publish on that result alone. The other NearSpec mode instead has a much higher resolution measurement of that feature. And so that's why we needed kind of those two measurements together. NearCam gives us this water feature, and NIRIS, it's really hard to see, I'm sorry, but the potassium feature is captured by NIRIS because it has high resolution at these low wavelengths here on the bluer end of the wavelength spectrum. And so hopefully this shows you how these four modes can be used in a complementary nature to each other. They have different wavelength coverages as well as resolutions and performances. And so using them all together, we can build up the most comprehensive view of an exoplanet atmosphere to date. What was interesting out of this work is we actually had some contrasting results between the four modes of the same observation. We found slightly different metallicities between each instrument mode. So they were reduced and modeled entirely separately. It's by different teams. Each paper is done by different teams, so completely different methods were used. And yeah, we ended up with a different metallicity, which means the content of everything that's not hydrogen and helium compared to hydrogen and helium in an atmosphere, and slightly different ratios of carbon to oxygen as well. There is ongoing work to perform a data synthesis and model synthesis, which will combine all four of these data sets together and then model them in a consistent manner. Hopefully that will help to iron out some of the discrepancies that we're seeing between the four instrument modes. So that was the ERS project. I want to take you a little bit sort of linked to what I was talking about before and to go back to talking about TRAPPIST-1. So TRAPPIST-1, several of the planets, if not all of the planets, have been and will be observed by JWST. And some of the first results from that are coming out. The ERS data was all public, but generally JWST data is proprietary. So we're kind of waiting for the results to come out as the teams get to writing the papers. So we had the thermal emission from the Earth-sized exoplanet TRAPPIST-1b using JWST just came out a few months ago. And essentially what that is when I've told you about the transit method where the planet passes in front of the star. This is when the planet passes behind the star. And so you can find out thermal information about the planet by when it's behind the star, you only have starlight. And when it's slightly either before or after the eclipse, you will see a reflection from the starlight, and you'll also see emission from the planet. And that can tell you a little bit about, for example, how the planet redistributes heat on its surface. And that can tell you if it has an atmosphere. So they managed to measure the temperature of TRAPPIST-1b with this work and found that it's about 450 degrees Fahrenheit. So probably much too hot to have an atmosphere. And then TRAPPIST-1c, the results just came out a month or so ago. And they also found that Planet C had a temperature of about 225 degrees Fahrenheit, also probably too hot to have an atmosphere, but they could only rule out a thick carbon dioxide atmosphere. They couldn't rule out a thin carbon dioxide atmosphere, but the results were consistent with both a thin carbon dioxide atmosphere and no atmosphere at all. But so far, it actually still remains to see whether Earth-sized planets around these low mass stars can actually host an atmosphere. And then this is just a little bit of a plug. So the Speculus 2 system that I told you about before, the second system to come out of the Speculus project, it is also called, this is the thing we do in astronomy where we have multiple names for the same star, but it's also called LP890-9, same system. There's a number of papers talking about that system I told you about because that planet C exists on the inner habitable zone boundary. And so Lisa Kalkneger and then a bunch of other people have written some papers talking about how we might be able to tell the difference between a runaway greenhouse scenario or a CO2 dominated atmosphere like Venus with only a small number of transits with JWST. So there are no observations of the system with JWST yet, but I'm hoping in cycle 3, which is coming up, that hopefully there will be a proposal in there. So I want to just take a little moment to talk more in detail about the work that I actually do as for the JWST project. So mostly this has involved developing software. So developing open source tools for the community to get essentially from transit light curve to transmission spectra. So this is involved a lot of modeling. And so our goal at CU Boulder was to develop a suite of packages to the community that everyone could use, from undergrad to master's student to PhD to professor. And so it's a collaborative effort from a bunch of people here at CU Boulder. And so one of the tools is called Chromatic, and essentially it allows you to load in a data set. So we call it a spectrophotometric data set, but that essentially means brightness as a function of wavelength and time. And so this is a data set directly loaded from the ERS data set. This is for a different planet, HAP P18b, but it allows us to load in this data set. It's in not very helpful units of Janskis, which is what they choose to put it into. So we might want to normalize this into something we can see more clearly. This is our transit here. So time is on the x-axis and wavelength on the y. So we can see, regardless of wavelength, we see a transit dip here between 0.8 and 0.9. But we have some weird wavelength systematics going on here. For example, there's an odd signature here, an odd signature here. So we might want to flag and remove some of those data points because we don't think they're real. We might want to bin our data. So like collect, we want to bin to a certain wavelength or time so we can collect more signal in a bin, and then we can build up the significance of a result. And then so get something that looks like this, a bit cleaner. If you had more than one period, you might want to combine those periods together and get a combined signal. And then Chromatic also allows you to produce a variety of different visualizations as well. So some people would find this more easy to understand than the last plot. This is kind of a two-dimensional where each color is a wavelength, different wavelength there. And so you can see the nice transit-like curve as we move across wavelengths. It also can let you do animations as well, where we step between different wavelengths. So we use Chromatic in a number of the ERS nature papers that I talked about. And this is just an example of the NIRCam paper. We used Chromatic to load in data from 3 independent data reductions and their models. And we can show the slight differences that we see between the three reduction pipelines. And that allows us to try and mitigate the systematics that are a function of the data processing and not actually in the data itself. The second tool, chromatic fitting, I promise I won't spend too much time on software, but I just want to talk a bit more about what I personally do. So chromatic fitting, which is the second tool that I'm leading development of, it essentially sits on top of chromatic and it allows you to fit different models to the data that you're getting. So we might want to, for example, combine a transit model here. So we know there's a planet in that system. This is simulated data that I've added a whole bunch of sneaky systematics into to make it look gross. So we might want to combine a transit with a ramp at the start of observations. So we see that often in space telescopes. We see ramps where the detector is sort of warming up to the observation. We might want to add a step in there. In JWST specifically, we are seeing these weird step functions because we get these, they're called mirror tilt events. So you have those 18 hexagonal mirrors, and it seems they don't quite know exactly what's happening, but it seems like there's stress releases that are happening every so often, and they cause a slight mirror tilt. And so you get a jump in flux sometimes in the data. We might have something that depends on time. We might have a function that depends on the position of the star on the detector. If your pixels are all going to vary in sensitivity, when the star slightly moves on your detector, you're going to see some corresponding effect in your light curve. And maybe something that depends on background because there's a contaminating source nearby. And so you can see finally, if you build up all these models together, you can get something that represents your data a little bit better. And the overall goal of doing this is to have just one fit where we can account for the spectral signatures that come from the planet's atmosphere, the star, and the instrument all at once. And you want to do this so you can get the most accurate parameters. If you have an instrumental systematic that affects the depth of your transit, then if you model those two things separately, you might get inaccurate results. But if you model them together, you can get the most accurate parameters and also learn about how your assumptions on some parameters affect other ones. And it also produces visualizations similar to chromatics, so, but with a model. So this is an example where I took data directly from JWST ERS, and then I fit a model to it, and then this is the residual we have at the end. Can produce animations, 2D light curves, and then most kind of crucially, a transmission spectrum, which helps you figure out what's in the planet's atmosphere. So both of these tools were developed alongside the JWST ERS program. They were improved and tweaked based on feedback from the ERS team, as well as we added different enhancements from what people in the team required. And so I think this is a really nice example of how open collaborative development can be really important, because all of this code is publicly available and free for anyone to use. So these are just the examples of plots from the NearCam, NEARES, and the Quick Look paper where chromatic was used. So we have visualizations in the NearCam and the Quick Look paper, and the transmission spectrum from chromatic fitting was used in the NEARES paper as well. And then I didn't talk about these slightly more physical models, but we also have an eclipse model, which is where that planet passes behind the star. And also we've added a model for cool spots on the surface of the star. So if you have a planet transiting its star and you have like a slightly cool region, you might see a bump in the light curve there. Which brings me to the challenges that I see to interpreting exoplanet atmospheres. So stellar contamination is known to be one of the biggest concerns we have for correctly interpreting transmission spectra. This can be an issue, for example, if we have a planet crossing over a spot, we're going to see that kind of bump that I just mentioned. But actually, more concerningly, if a planet passes a region of a star that isn't spotted, and spots being these cooler regions on the surface that we see on the sun as well, what's more concerning is that we assume when we do transmission spectroscopy that the surface of the star is completely uniform and completely homogeneous. In reality, we know it's not. And so if the light that goes through the planet's atmosphere is not the same as the average of the star, we're going to end up with these weird systematic, weird effects because they're spectrally different. One is hotter, one is cooler, so they're going to be slightly shifted in wavelength. So there's been a lot of work on this. Ben Rackham wrote a couple of papers on this. They call it the transit light source effect. And essentially the conclusion of that was that he showed that for these red dwarfs, the ones that I'm particularly interested in, the effect of this contamination, or the blue line here, sorry, that's a lie, the brown line here, is on the order of the planetary features that we care about. And so what that means is that the stellar contamination can actually mask or even mimic a planetary feature in our atmosphere because it's very, very hard to disentangle the two. They go into a lot more detail on this. There's called the SAG-21 report, where they talk about the effect of stellar contamination on transmission spectroscopy. They talk about this as one of the potential issues, but also sort of mitigation strategies, like what can we do moving forward to try and get rid of this effect? How can we account for it? And essentially, one of the key takeaways is that our stellar models just aren't quite there yet. Like, we don't have good enough stellar models for the data. Additionally, they talk about how we could maybe use observations of the sun to be able to apply that to other stars out there. And we're actually already seeing the stellar contamination come into play with JWST observations of an exoplanet GJ486b. They have this data here, this white data, and they actually found this transmission spectrum that they measured was both consistent with a water-rich planet atmosphere and stellar spots on the surface of the star. So they could not disentangle those two models, meaning that essentially they don't know what to do with the data. A second major challenge is clouds. So say that the star is perfectly homogeneous, there's no spots, everything's great. You might not be able to see what's in the atmosphere because there are clouds on the surface of the planet. So these clouds act as like an opaque layer, and essentially we can only see everything above that layer. And so if you have clouds like thick clouds or clouds high in the atmosphere, we're really going to be limited in what we can see. And so this can dampen your transmission spectra and the features in it, or even give you a flat transmission spectra. You've already seen this with Hubble. And there was a paper that was released a few years ago where they essentially said for these red dwarfs, clouds can lead to a 10 to 100 times increase in the number of transits you need to detect water features with JWST, which is really concerning for a telescope, which has very precious time. And finally, I mean, there's many more challenges than this, but these are just 3 that I've identified and I'm mentioning today. Say that the star is completely homogeneous. Say that we don't have clouds and everything's great. We can get a perfect transmission spectrum and still not be interpreting it correctly. So to get from transmission spectrum to this amount of CO2 in the atmosphere, we use models, chemical atmospheric models. There is actually an accuracy limit of those models that is an order of magnitude above the precision of JWST. So we're limited kind of on all fronts here. And this is another case, I think, where because the precision of JWST is so high and we're now in this like new era of atmospheric chemistry, we're kind of pushing up against the boundary of our models. Like our data is outpacing our models essentially. And so I think the next couple of years are going to be really exciting for trying to deal with some of these issues and also make advancements both in observations and in theory. So in conclusion, to try and conclude all that information, we can and are detecting prime candidate exoplanets for atmospheric follow-up. Specifically for temperate terrestrial planets, I'm hoping I've convinced you to look around low mass cool stars, these red dwarfs. We're in the era of JWST. There's also a number of extremely large ground-based telescopes that are going to be coming online in the coming decades that will also be able to do really cool science from the ground. The first results from the ERS program demonstrate JWST's precision and the power of its wavelength coverage. And we have several exoplanet atmosphere firsts, like the first detection of carbon dioxide and sulfur dioxide as well. And there are a number of major challenges to correctly interpreting exoplanet spectra. But I don't think that's too negative a note, because essentially what it means is that the instruments are just so powerful that we've never come across these issues before. So I think it's actually a positive. And so we need tools to be able to, at least for the stellar contamination part, to be able to model the planet plus the star plus the instrument all at once. And so that's my little plug for my tool, chromatic fitting. So thank you very much for having me. And if you have any questions, I'd be happy to take them. Thank you. Oh, yes, thank you. I always forget to do that. I don't know if Brian's going to come back in or. Sure, yeah.
Yeah, so my question is, when the telescope that we have, was this, where do you get more information from? It's phase, and you know, and how accessible is that information?
Okay, yeah. So the question is, how do you, so yeah, correct me if I'm wrong, how do you get more information to deal with some of these issues? Is it from the ground? Is it in space? And was there a final part to that? Sorry.
And then how accessible is it? You know, because somebody has the information, you have to get that data to analyze it.
Yes. Okay. And so how accessible is that information? I think all of the above. What I'm most familiar with probably is the stellar part of things. But actually I think it's applicable for both the stellar and the limits in the opacity models. So that's how you get from the transmission spectra to abundances. Both require a lot of experimental work actually done on the ground. So the stellar stuff, yeah, what you can do is you can do lab-based experiments using light that kind of simulates a star, and you can use that to try and replicate, create stellar models. We can use, so that's sort of your lab-based work. I'm not an experimental person, so forgive me, I don't know a lot of detail more than that. You can use space-based observations, for example, or observations of space, I should say. So for example, for stars, what you could do is you could build up a big catalog of spectra of lots of stars, and you could use that to start making inferences about, well, if a star has this temperature and this magnitude, it should look like this. And we can start building up empirical spectra based on that. So we have spectral models We usually use Phoenix at least in my field, but we're actually finding that the inaccuracies in those are noticeable in the JWST precision. So building up like empirical spectra is one of the ways they've suggested doing it. How accessible all of that is sort of depends on the team that does it, unfortunately. I like to implement an open science, open source approach in what I do, but it really depends on the team doing it. But I would hope that if a team did it and then didn't share it with anyone, then someone would come along who would share that information. I hope that's helped answer the question. Sure. Okay, the question is, with all this new technology, have we discovered any habitable planets with atmosphere? I don't think so, as far as I'm aware. We're just like struggling also because, so the reason I'm talking about these low mass stars is that's the only place that we're really able to find a large number of planets in the habitable zone. Because yeah, with a sun-like star, we're going to have to find planets that are much bigger than the Earth to be able to detect them. And then getting something that's in the habitable zone, we're waiting a year between transits, and you usually take 2 or 3 to confirm a planet. So we're waiting 2 to 3 years for just one planet, which is very difficult. So I don't think so. I think that would be big news if that's happened and I have missed it, but I think that we don't know of anything yet. I don't think we have a clear detection of an atmosphere on an Earth-sized planet yet. I might have someone in the back. Question is, how close are we to finding a planet with liquid water in the atmosphere or on the surface? On the surface, oh gosh, that feels far away. I mean, I think we can definitely find water vapor in the atmosphere. We're doing that already. Finding it on the surface, we might not be too far away from that. I have to say, I'm not sure if I know the jump in precision we need to be able to get to the surface. We're looking high up in the atmosphere right now. So I don't have a number in my head of we need to get X times better to get to the surface. Using the eclipse method where you go behind the star can be really interesting. It gives you, the atmosphere just blocks what's on the surface. So if you find an atmosphere, it's going to be hard to see down to the surface, I think. So I'm afraid I don't have a good answer for that one. Feels like at least 10 years, let's say. I'm pulling that number out of nowhere, but let's see that. Yes. Okay, the question is, sorry. Okay, the question is, do I have a prediction of how many more exoplanets will be found? I mean, do you have a time frame for that? Well, it's exponential. That's the problem. That's a, predicted. Yeah, exactly. Extrapolating that is going to give infinite, I think. I mean, we know of about 5,000 currently. There are also a number of, I think, a couple of thousand test planets that are candidates but haven't been confirmed, which are just sort of sitting there. So those aren't counted in that 5,000, I think. Those are just sitting there. So there's already potentially another 4,000 that just haven't been confirmed. And that's all, yeah. So to Kepler, it's not quite exponential, I should say. There's jumps. So Kepler was obviously the first big jump, and then TESS is the next big jump. But assuming that continues, and there's more and more space telescopes, like Plato is coming, and that will discover a lot more. I don't think there is a limit to how many planets, but yeah. I would. Yeah, exactly. We're just going to be finding smaller planets. So there's stars that we've looked at so far where we're limited in the size of planets. So we've found a Jupiter-sized planet, but maybe there's more planets we're just not able to detect. Yeah, so that's probably as good as I do. Are there any online? I don't know where one's going, but okay, yes. Hi. Okay, so the question is, how far away could were you saying red dwarf star? Because the question is, how far would a star hosting an Earth-sized planet, how far could it be away to observe it? And so with Speculus, the project I was involved with, we had a cutoff of 40 parsecs. I don't have the conversion between parsecs and light years in my head right now, but that's kind of considered to be like local stellar neighborhood. It's like pretty close. How far it drops off? Yeah, it drops off quite quickly. How far, like the brightness you can observe. Like these low mass stars are already very challenging to observe because they're bright, they're faint in the visible and brighter in the red, and so they're already faint by most telescope standards, including Speculus. And so I think that 40 parsec limit is in place so that we only get, I don't think we could observe much beyond that. I think it would get too faint and the precision would be too low. You would need to probably go into the infrared if you wanted to go further. That gets way more challenging on the ground. Speculus was implementing an infrared camera last I heard, but when I started the postdoc, I stopped being involved with projects. So I'm not sure how far that's gotten, but it gets way more complicated in terms of the water vapor in the atmosphere. So you need an infrared space-based telescope to get further than that, I think. Yeah, I'm afraid I don't have a good number for you apart from, I think that number was chosen, the 40 parsecs was chosen to say essentially it's not going to be worth us looking any further than that. Yes. Yes. The question is, have I developed a chromatic fitting or used chromatic fitting to the data, our Earth around our sun using a telescope that's already out there? I have not. I have not, and I have not even thought about it, to be honest. But that's a interesting thing to think about. Yeah, no, I hadn't considered that before. I am looking at putting, this isn't quite related, it's a little tangential, but I am looking at putting an Earth's atmosphere model in for if we want to observe from the ground. We will also have to not only deal with the planet, the star, the instrument, but also the Earth's atmosphere in there as well. So that's another model I will add, but it's not quite answering your question. I haven't considered that before. This answers the question. Yes. Oh, this is a great question. What is the relationship between flare frequency and stellar mass, or like cool dwarf mass? I actually did a whole paper on this, so this is very exciting for me. Yes, that's a great question. Thank you. It's like I planted it there. Yeah, so we're essentially, Speculus is like the only observatory that could do that study. So previously, before Speculus, so from tests and other surveys, they found that the flaring frequency got stars flared more frequently as we got to lower mass stars. And then the work that I was doing with Speculus, I could go to even lower mass stars. So that they were finding that an increase in the frequency to about M4, M5, which is the limit of what tests can see, and that's about, I think, 3000 Kelvin-ish stars, maybe 0.15 the Earth mass, the sun mass. But we were finding with Speculus that the flares actually tend to die off as you get even later. So there's some peak in flaring frequency or in the mid M dwarfs, and then it actually dies off as you get more towards brown dwarfs, which is good and bad, because the good part is that you don't have a planet being attacked with flares from its star and it's close, so that's an issue. The bad part is that flares actually could be really beneficial in delivering UV energy or visible light energy, because those stars are so red, they're not going to be giving a lot of UV or blue light to the planet. And that can actually be, UV light can be really good for photosynthesis, for certain chemical reactions that we have here on Earth. And so it's good and bad, I guess. But yes, generally flaring frequency seems to peak around mid-M dwarfs. So yeah, those sort of 0.15 mass, solar mass stars, and then fall off. So although, sorry, just add more because it's exciting for me. TRAPPIST-1 is actually especially active. It flares a lot. And so, yes, it's more active than the average M8, which is the type of star that is. Yeah, they can vary a lot, but yeah, TRAPPIST-1 actually is especially active, which is not great for people trying to look at the observations. Do we have time for, sorry, do we have time for more questions? Should I?
Maybe one more question.
One more question.
And if folks have questions,
Yeah. Okay, yes, thanks.
how would you think answer? So, all the students, all the students studying, find the closest the last year.
The question is the ultimate goal of my field of study to find Earth 2.0 for us to, for mankind to go to? Depends who you ask, I think. I think a central goal is to find a planet like the Earth. I don't think my motivation is necessarily finding one. I think that adds a whole bunch of extra complications of having to figure out space travel and traveling the speed of light and all those sort of things that seem quite complicated. But I think that being able to find a planet like the Earth, at least one that we think can be habitable in all the ways we can figure that out from here, I think is a central aim for a lot of people. Like trying to figure out what, if we were able to find a planet like the Earth, it could tell us so much about our own home. Like it could tell us, is there life out there that looks like us? Is there life out there at all? Are we a common outcome of planetary formation, or are we a fluke? And I think that those questions are more my driver. I'm sure there are people out there who want to find Earth 2.0, but to go there. But I think that's a much bigger question, as whether we go there and whether we have time to get there before humans.
One of the fascinating field of study, you get caught in the join the research so much that you ultimately go instead of just challenging, trying to figure out what to try that. But or is that what you need to tell? So you keep the fun.
No, probably not. I think is the answer to that. No, I don't think to get funding, I really push the fundamental scientific questions about the origin of life and not about trying to get humans to another planet. But that good? All I have time for? Great. Well, thank you everyone for listening.
And folks, it looks like half the sky has clouded up. So I'm not sure we're going to be able to do stargazing tonight, but we have put the sun in one of our special solar telescopes. So if you would like to go up and look at the sun before it sets, you're welcome to do that. I'll invite you to come out into the lobby here, and we'll take you up to the observatory. And if you just want to go see the observatory, you're welcome to visit up there as well. Thanks so much for coming. Have a good weekend, and we'll see you in August.